The learning objectives for this segment are to calculate Kb for a base given the Ka for the conjugate acid and vice versa, and calculate pH and other reaction equilibria for weak bases. So a reaction of bases with water. So the standard reaction of a base with water, it's a base plus H2O, and that gives you OH minus plus the conjugate acid of the base. So this is a little different in this case because we are creating OH minus from the water rather than losing the H plus from the acid. So what is the equilibrium constant for this going to be? Well, it's going to be what's on this side, Kb, we call the Kc for this reaction Kb for K base. It's going to be the concentration of BH plus times the concentration of OH minus divided by the concentration of the base. And then we treat liquid water as pure, and so we don't take that into account. Okay, so that's what we're going to be dealing with. Now the interesting thing, there's a close relationship between weak bases and acids. So Kb, there's this expression there. So Kb's, you have a lot of relatively weak bases that are organic. Essentially, you've got a lot of carbon, nitrogen systems. A lot of times you'll have a nitrogen with like an NH2, and that tends to like to pick up an H plus for the water, creating OH minus. So these are a lot of common weak bases. There's a lot of them out there. And then each of those bases has a conjugate acid. And you can calculate the Ka of those conjugate acids. As you might imagine, if you have a relatively strong base, the Ka, something that likes to pull H plus away from water, then the conjugate acid will be relatively weak. It won't really like to give that H plus back to water. And so you see a lot of, there's a pattern there, and this is not an accident. So if we're looking at the relationship between Ka and Kb, so we write the Ka, right? It's A minus plus H3O plus, the product of that over HA. So if A, and then when we calculate the Kb of the conjugate base, we have to make sure we have things labeled correctly. If A minus is the base, then HA is the acid. And so for Kb, then the conjugate acids, the protonated acid will be HA, and then A minus is the base, like the charged thing is the base here. And so what is Ka times Kb? Well, it ends up that there's a relatively simple relationship here. Let's look at this. So our Ka, we write that as A minus times H3O plus over HA, that's the expression for Ka. And then we multiply that. Let's write this more explicitly. Ka times Kb. There's our Ka, and our Kb is HA. That's the conjugate base of A minus, OH minus over A minus, okay. But notice that this cancels and this cancels, and so we get H3O plus times OH minus. But we know that that is, right? That's just Kw, which we know, which is going to be 1.0 times 10 to the minus 14th, assuming we're at room temperature. So Ka times Kb, and again, it's just not any Ka and Kb. It's Ka and Ka of an acid and Kb of its conjugate base is going to be equal to Kw. And this is not surprising because if you write out the reactions, HA plus H2O is in equilibrium with H3O plus A minus. That's our acid reaction. A minus plus H2O goes to OH minus plus HA. So that gives us 2H2O because the HAs cancel out both sides. OH minus plus H3O plus, right? That's just the equation for the autoionization of water, which is of course the equation for which Kc is equal to Kw. So this is a general mathematical relationship just because of the relationship between conjugate acids and conjugate bases.